this time around, we want to show that we can get the same result using our new chain rule as we could if we were just to substitute in and do all the work on the front end before differentiating with respect to a single variable. And the reason we do this is mostly just to make sure that we've covered all the bases, but it's also to show that sometimes it makes the sense to put in that work up front, and other times it doesn't make sense at all to do that. So we want to see, kind of what our trade-offs are here. So given this, w equals xy plus xz plus yz, where x, y, and z are all parameterized by t, let's find dw dt using the chain rule. So to do that, let's go ahead and write out what that means and what we need to do to get there. So to get there, we say that dw dt, recall that the sort of shorthand way to do this is I've got that this is a function of 3 variables, so I'm going to go ahead and write the partials out. And I'm going to say to myself, okay, if I have this and I was trying to get this, I need a t on bottom and I need to get rid of an x. So I would say, all right, that makes that cancel and that gives me what I need on bottom. That makes the y cancel, that gives me what I need on bottom. That makes the d cancel, dt is what I need on bottom. Again, these are not fractions. They're not. And there are cases where this is invalid, but for practical purposes, I guess, this is going to work. So now that we have this, what we see is we need 6 different pieces to put it all together. So let's go ahead and start working on that. If I say the partial of w with respect to x, well, that means I get y plus z, and that goes to 0. The partial with respect to y, all right, I get x, 0, z. And the partial with respect to z is 0, x, y. But the problem is that, again, we always want this in t. So we need to convert these to functions of t. So y plus z is t squared plus t minus 1. X plus z is 2t minus 1. And x plus y is t squared plus t minus 2. So now, I need to get the derivatives with respect to x, y, or of x, y, and z with respect to t. So I need to get dx dt. That's 1. I need to get dy dt. And that's 2t. And I need to get dz dt, which is also just 1. So putting all that together with these components, so these match, and those match. So I'm going to do a little head math to save some time and space. I get t squared, 4t squared, and t squared gets me 6t squared. I get t minus 2t plus t. Well, then those cancel. I get negative 1, negative 2. So I get 6t squared minus 3. So that's kind of our thought here. Took a little bit to get there. Okay, well, let's go look over on this one. We need to substitute in beforehand. So I need to take this equation and go ahead and plug in what those values are. So xy is t minus 1, t squared minus 1, and xz is t minus 1, t, and yz is t squared minus 1, t. All right, so we multiply that out. T cubed minus t squared minus t plus 1 plus t squared minus t plus t cubed minus t. So that's actually not too bad. Let's go ahead and combine like terms here. We've got 2t cubes. T squareds cancel, so there's no t squareds. Negative 1, negative 2, negative 3t plus 1. So now that we've gone ahead and gotten that, we can take the derivative of w with respect to t. So we get 6t squared minus 3, which is exactly the same as we got here, which hopefully is what you expected, because regardless of how you get there, it gets the same answer. So why are we doing this? Well, we're doing this to show that in this particular case, and from my perspective, it was significantly easier and faster to do it this way. There's no doubt about it. So when would it be faster over here? Well, a really good case for that is when you have like really nasty functions, but they are maybe only in a single variable. So like your partial with respect to x, if there was a bunch of y's and z's, it just falls out to 0. You still maybe have to take care of it over here, but a lot of times it's practice and intuition. You go, okay, that's definitely easier to go ahead and differentiate versus maybe doing it over here as some sort of, if these functions were really nasty in t, you'd prefer not to have to differentiate those. So realistically, I guess I would say that take a look at what these functions are, and if these functions are really nasty, don't do it this way. If these functions are really nasty, do it this way. So you're just kind of picking your poison.